Okay, so our last trend is about electronegativity. So electronegativity is the concept that if you have a chemical bond, the electrons are likely to be more attracted to some atoms than they are to others. In this particular version, which is from your textbook from Chem Libre, we will see that the highest electronegativity value is fluorine. We don't have any noble gases on here because they are very difficult to measure in a compound. They don't like to react. So we just kind of cut them off of the electronegativity version of the periodic table. And so this number, 4.0, is the highest value for electronegativity of any atom in the periodic table. That means that fluorine, if it's in a compound, in a bond, has a tendency to pull the electrons towards it really very strongly, no matter what it's connected to. So we notice that if you look across the period, lithium has a value of 1, and then it gets bigger and bigger until you get to fluorine at 4. So the trend follows ionization energy across the period. It matches. And that kind of makes sense. So if you have lithium in a bond with something, it's not going to pull the electrons towards it very strongly because the ionization energy is pretty low, right? So those things seem like they make sense. And going up and down in the table, we see, again, fluorine is the highest, so AT is the lowest in this group, and that's true of every group. So 2 versus 3.5, 1.9 versus 3. So it's getting bigger going toward the upper right part of the periodic table. That means that our friend francium down here is the most metallic thing in the periodic table. So anything that gives up its electrons fairly well, doesn't pull them in a bond, is going to be more metallic in character. So francium is the most metallic. It's the lowest electronegativity of anything in the periodic table. Okay. So, turns out, up until now, we've used the idea that non-metals connected to each other will form a covalent bond, and metals and non-metals will be an ionic bond. That's too simple to explain the behaviors of actual chemicals. There's a lot of transition metals, for example, that form covalent bonds. In fact, some of the work I did on cancer research when I was in graduate school relies on the fact that platinum forms covalent bonds with RNA and DNA. If it didn't, the medicines that we use to treat some cancers wouldn't do anything. So it has to be a covalent bond. It has to be nice and strong for that chemistry to happen. So now we want to use electronegativity as the way to determine when things are covalent and when they're not. So here I've made a graphical representation of this, and it's important to understand that if you go look at different textbooks, different YouTubers, whatever, the cutoffs are different for each individual. There's not a hard and fast rule. For our purposes, we're going to say anything that has an electronegativity difference below 0.4, we're going to count as nonpolar. So nonpolar meaning the electrons are shared equally between the two atoms. Our example of nonpolar here is nitrogen. 2 nitrogen atoms connected to each other. And so if we look at the electronegativity table, we'll see the value for nitrogen is 3. And so 3 minus 3, because that's what the atoms are, is going to be 0. So that is a nonpolar covalent bond, meaning electrons are shared equally. On the other hand, anything with a value that is bigger than 4 but less than 2, we're going to call that polar covalent. So the electrons are still shared, but not equally. So here we have oxygen, which has a value of 3.5, and hydrogen, which is 2.1. So the difference between them is 1.4. That's right in the middle of our polar covalent region. What this means is that the electrons shared between an oxygen and a hydrogen are going to spend more time towards the oxygen than they do towards the hydrogen. Okay, so this is what it means to have bond polarity. So when a question asks you about type of bonds, polar, nonpolar, ionic bonds, you want to use electronegativity. Okay. So if you have a value that is bigger than 2, we're going to call that ionic, which means it looks like this. The sodium has completely given up its electron to the fluorine. It's not going to get it back. They're separate particles now, and that's what an ionic bond looks like. So for example of something where we would have predicted it to be ionic based on our prior learning, if you actually look at the numbers, it is not an ionic bond. Okay, so again, we get these numbers off of the periodic table from the lecture notes that has electronegativities listed, also in your textbook. So chlorine is 3.0, copper is 1.9, so when you subtract them, you get a difference of 1.1, which again is not ionic. It's going to be polar covalent bond. And the chemistry of copper agrees with this. So for carbon and hydrogen, we have a value of 2.5 for carbon and 2.1 for hydrogen. So it is right on the border between nonpolar and polar covalent, and how that gets classified depends on the person very strongly. For our purposes, again, if it's 0.4 or lower, we'll say it's nonpolar. If it's bigger than 0.4, we'll say it's polar. Carbon and oxygen, carbon again is 2.5, oxygen is 3.5. So we'll take the bigger one and subtract it from the smaller one, and so we get a value of 1.0. This tells us anytime we have a carbon-oxygen bond, the electrons are going to spend more time on the oxygen than they do on the carbon, and that dictates a lot of the chemistry that can happen there. Okay, so you can do the same thing for sodium and chlorine and strontium and fluorine. See if they're actually ionic or not. Okay, so to summarize the trends, this is actually chapter 7 for us, but to summarize the trends in the periodic table, first off, we have the idea of metallic character. So again, that means ductile, conductive, malleable. You can form it into wires or sheets, etc. That's what makes something a metal, shiny. The most metallic element, the highest metallic character, is going to be francium, bottom left corner. Because francium gives up its electrons the easiest, so it's going to have also the lowest electronegativity. And the lowest electron affinity and the lowest ionization energy. Those are all characteristics that give elements their metallic character. And so that means on the other corner of the periodic table, helium is the least metallic element. It does not like to give up its electrons at all. We also looked at atomic radius. Remember that things get bigger going down a group. Not down a period, they would get bigger down a group. And they get smaller going across the period from left to right, which means helium is the smallest and francium is the biggest. Our last two trends, ionization energy. So the things on the left side of the periodic table tend to have low ionization energies, and the things on the right tend to have high ionization energies. Similarly, stuff on top is holding onto its electrons tighter, so higher ionization energy than is on the bottom. Our last trend was electronegativity, and it follows that same pattern for the same reasons.